In this lecture, we're going to describe each of the geometric properties of cubic unit cells to get ourselves set up to do calculations later in class. Crystalline solids are characterized by a regular, repeating arrangement of atoms, ions, or molecules in their structure. Each space occupied by an atom or ion is called a lattice point. The smallest repeating unit in a crystalline lattice is called the unit cell. You can think of the unit cell as an individual doll in a long, unbroken paper doll chain. The three types of cubic unit cells are characterized by equal edge lengths and 90-degree angles at each corner to form a cube, hence the name. Before we examine each type in depth, let's look at how to count atoms in a unit cell. Unless an atom or ion is located in an interior position, atoms are shared between neighboring units. For example, on the left, I have an intact unit cell. On the right, I've sliced off any part of the atom or ion that isn't located inside the unit cell we're examining. Since this atom or ion is located on the corner, it is shared between 8 unit cells. That means that at most, only 1/8 of the atom is contained in any one unit cell in a corner position. If we look at the intact blue and red unit cell on the bottom left, we see that the red oxide ions occupy the edge positions. Edges are shared between 4 unit cells, so at most, an edge atom will contribute 1/4 of an atom to a unit cell. If we look at the blue and red rhenium oxide unit cell on the bottom right, the blue rhenium ions occupy face positions. In this sliced and diced version of the unit cell, we can see that the face ions will only contribute half an ion because it's shared between 2 unit cells. Now that we have a basic understanding of how to count atoms and ions, let's look at the main features of the cubic unit cells. If we take a minute to count atoms in our cubic unit cells, what do we find? A simple cubic unit cell contains an atom on each of the 8 corners. A corner position contributes 1/8 of an atom to a unit cell, so a simple cubic unit cell contains 1 atom. A body-centered cubic unit cell has an additional atom in the body-centered position. This means it contains 1 more atom than a simple cubic unit cell for a total of 2 atoms. The face-centered cubic unit cell contains an atom on each of its 6 faces. A facial atom contributes half an atom to the cubic unit cell, so if we add the 1 atom contributed by the corner positions, we have a total of 4 atoms. The coordination number is the number of next-door neighbors an atom has in a cubic unit cell when you consider the extended structure. When we're counting nearest neighbors, we look at the innermost atom in a block of 8 cubic unit cells and consider who the closest neighbors are. In the case of this simple cubic unit cell, the coordination number, counted from the red atom, is 6. If we apply this coordination number counting process to a space-filling model of the unit cell, we see that we need the extended structure of 8 cubic unit cells to count off the coordination number. It's not as easy to do in this type of model, but this is a common way of representing the cubic unit cell. When we move to the body-centered cubic unit cells, the atoms or ions in the body-centered locations are usually given a different color to emphasize their place in the cubic unit cell. When we move to the extended structure, we see these body-centered atoms are the nearest neighbors to our central corner atom. Since there are 8 cubes, each with 1 body-centered atom, the coordination number is 8 for a body-centered cubic unit cell. In the space-filling, face-centered cubic unit cell model, we see that only some of the 6 face-centered atoms are counted as nearest neighbors to the central blue atom in the middle of the extended structure. Most textbooks don't even attempt to show all 12 connections, so once you get to this structure, it's probably best to just take this value on faith and commit it to memory. The edge length, denoted A in this figure, is defined in terms of the atomic or ionic radius r of the element in question. If you're interested in how each of the edge lengths are calculated in terms of r, the derivations are shown. Note that you will not be held responsible for calculating the edge length in terms of the radius for the purposes of this class, but I wanted to introduce it to you because you're sure to run across it in your reading. The packing efficiency is the percentage of space occupied by atoms or ions in the unit cell. While I'm giving the actual percent volumes of occupied space in each cubic unit cell here, don't feel as though you need to be able to quote these exact numbers. Rather, I'd prefer that you be able to give the relative packing efficiencies, low, medium, or high. This table contains all of the information you need to have memorized for the exam. Ionic solids present an excellent opportunity to review our unit cell information. To start, how many cesium and chloride ions are in this unit cell? We see that we have one cesium cation contained wholly within the unit cell, while we have 8 chloride, 8 chloride ions on each of the corners, contributing 1/8 of a chloride. And then our 1 cesium, so our formula will be CsCl. What about for zinc blend? We have 4 zinc cations contained wholly within the unit cell. We have sulfur occupying 2 different positions, the corners and the faces. As we saw with cesium chloride, the corner sulfurs will contribute 1 total sulfur ion, while the 6 sulfur atoms occupying the 6 faces of the unit cell contribute half an ion each for an additional 3 sulfur atoms. Knowing that this unit cell contains 4 zinc cations and 4 sulfur anions, what is the correct empirical formula for zinc blend? Is it Zn4s4 or ZnS? Recall that the empirical formula of a chemical compound is the simplest integer ratio of atoms present in a compound. For this reason, the correct answer is ZnS.